I work at the Melfis, but I'm also doing a PhD at Exeter. I'm going to start my talk in the same way as Thomas. So this is a work in progress. I would say this is more towards a comparison of time parallel across the method deferred correction schemes. So part of this is a preprint paper of serial SDC methods, and then the next is a comparison of two parallel in time. Okay, so an outline of my talk. So I'm going to start off giving you an introduction, showing sort of where I'm coming from. So I work at the Melfis. We are currently developing Gung Ho. This code is implemented in Gusto, and then I'm going to talk a little bit about compatible finite elements. I'm then going to probably skim through the deferred correction overview because you've seen it twice already. And then I'm going to go through some classic dynamical core cases and the results and give a summary. Okay, part one. Okay, so Elfric, Atmosphere, and Gung Ho. So our next generation model, so the previous one is called the and the new one is called Momentum now, but the atmospheric component is Elfric Atmosphere, and at the heart of it, the dynamical core that solves the compressible Euler equations is Gung Ho. So it is, as previously, non-hydrostatic, but we're moving away from finite difference on a latitude-longitude grid to a cube sphere horizontal grid using compatible finite element methods. So we follow a similar staggering to the C-grid staggering if you've seen it before. And so our cell centers, you have density and exner pressure staggered vertically. In Charney-Phillips staggering, you've got potential temperature and moisture variables, and then winds is flux through faces. The Melfis for a very long time used a semi-implicit semi-Lagrangian method. It essentially allows you to take really long time steps, and so it's quite efficient. We've moved away from semi-Lagrangian transport to a different variant, which is a finite volume explicit transport, but is called flux form semi-Lagrangian. It works in a similar way and allows you to similarly take large time steps. We use an iterative semi-implicit time stepping, so evaluate our transport, and then we have this kind of inner and outer loop structure and have this implicit solve in the center. So I'm going to compare the IMEX STC, which I'm going to talk about, to this. Okay, what is Gusto? So Gusto Gung Ho. Gusto is kind of similar-ish to Daedalus, I would say. So it's an atmospheric dynamical kit. It's built on top of Firedrake and is essentially, so it's a finite element, which is a finite element library for solving PDEs. This is not my picture, this is Tom Bendel's picture. So essentially it has a bunch of different transport schemes, time steppers, IO, different equation sets, so compressible Euler, shallow water equations, different mesh types, but all of that is built into Firedrake, and some physics schemes, so not all, but a few idealized physics schemes. And essentially, it ideally should allow for rapid prototyping.
What's the RAM complex doing on the box?
Oh, so that's the next slide. So it's all compatible finite elements. So it sets up your different function spaces automatically if you just give it one. Okay. So the link between Gung Ho and Gusto, apart from the fact that the names are very similar, is compatible finite elements. So it's essentially a type of mixed finite element method, and function spaces are part of the discrete de Rham complex. So you've got H1, HK, HDiv, and L2. So your scale is L2, and essentially it obeys discrete vector calculus relations. So curl of grad of a scalar is 0, and div of curl of a vector is also 0. So the way the essentially methods we are using, they mimic the kind of C-grid staggering that you'd get in finite difference methods. So this avoids computational modes. So in our model, we don't have any kind of additional diffusion apart from that from the numerics or divergence damping, and you get good discrete dispersion. Okay, so part 2, deferred correction over. So I'll start with the motivation and then talk about the equations. So why would you want to use STC? What's an alternative to the popular Runge-Kutta methods? And you can essentially achieve arbitrary high order without condition constraints, which is good for IMEX schemes. There is existing research, which I'll use some of, into time parallel SDC. And potentially for us, so at the Met Office, we use a unified model, so the same model for climate, regional modeling, and NWP on a global scale. And it doesn't change between them. So being able to change your order easily just by changing the number of nodes or correcting iterations might be kind of useful. So the equations I'm solving here are the compressible Euler equations. I've labeled, so I'm using an IMEX scheme. I'm essentially treating transport terms explicitly, non-transport terms implicitly, physics terms explicitly, and then I'm treating the vertical advection term in density and potential temperature, so the second and the third equation, implicitly, mainly for stability reasons, because they're kind of associated with gravity waves, and that's having stability problems running the baroclinic wave, which we'll see later. Do I skim through this one or not? I'll skim through this one relatively quickly.
We've got
So-
plenty of time.
Yeah, but people want to go home. So I'm going to go through two ways of looking at SDC. So the first one, you're starting with your Picard integral form, your error equation, so your actual solution minus your approximate solution, and which is delta, and the residual, which is epsilon, which is your solution at time 0 plus the integral of the right-hand side of the approximate solution minus the solution. I'm going to quickly jump through this, but essentially you can do a bit of manipulation of this and end up time stepping the error in this way. So you've got error n plus 1 equals error n plus the residual n plus 1 minus the residual n plus delta t times g, where g is this difference between the approximate solution plus error approximate solution. This term here is this here, and we can essentially integrate, so we can evaluate this integral using quadrature and integrate Lagrange polynomials, as you kind of saw before. And the end result, so this is previously you've seen the 0 to node formulation. This is the node to node that essentially goes from u at node n plus 1 iteration, correction iteration k plus 1 equals k plus 1 plus d tau, which is your quadrature node spacing. This is implicit rather than IMEX, but f of n plus 1k plus 1 minus f of n plus 1k plus your error integral term.
It would be much easier to read if the error was called epsilon.
Yeah.
And the
Yeah,
residual was
I
called
thought the exact same thing, but in the original paper, that's what it is.
You don't care about the original paper.
Yeah.
Just use a notation I can easily parse.
I would agree though. Error, yeah. Okay, so this is the one that you've seen before. So this is essentially you're doing your quadrature, which is like a implicit Runge-Kutta method, and you end up writing it in matrix vector form like this, and you use a Richardson iteration and then precondition it. I'm just going to flick through this, and common choices. So if you're doing implicit, you can use the implicit Euler Q delta matrix, or you can use this LU trick, LU factorization, which is quite fast. And in the 0 to node formulation, it's un plus 1k equals u0 or un, and you've got a sum up to n plus 1 here because it's implicit, and your correction. Okay, so I've got a little animation that just shows what happens. Here, this is using essentially an implicit method with 2 nodes. I mean, they look equispaced, but you could say that we're Gauss-Legendre nodes in the middle, and then 2 correction iterations. So it kind of works in a sort of predictor-corrector way. So you get your initial solution on your quadrature nodes, u01, u02, and then you use the first correction sweep on it, second correction sweep on it, and then finally update it to get your solution at Tn plus 1. Okay, so hello SDC. So essentially, I'm parallelizing with 2 different ways. So the first is the way that you saw before, which has this SDC in Q delta form and uses a diagonal Q. And the second is revisionist integral deferred correction, which is essentially a pipeline variant of SDC. Okay, so here if I'm doing explicit, I'm using the non-stiff Q delta matrix C on the right, and then if implicit, it's the flex one. So these are essentially Gaia and Thiebaud's from Gaia and Thiebaud's paper, and they minimize the spectral radius of the iteration matrices for the stiff and non-stiff. So Riddick works quite similarly to STC, so you kind of have it more in this node-to-node formulation at the top. The main sort of difference is your integral term is treated slightly differently, so you can pipeline your correction iterations. You use uniformly spaced nodes instead of other choices like Legendre or Radal, and Euler steps are used to discretize. And well, at least so what I see SDC is normally you have a given time step and you set up your quadrature nodes in that time step. And normally, not always, you have less nodes than you do correction iterations, because you want to correct to the order of the underlying quadrature. Whilst revisionist integral deferred correction, you normally have a lot more nodes than correction iterations. So because you're parallelizing across the correction sweeps instead of parallelizing across the nodes, you need at least k times k plus 1 over 2. And so you set up these j intervals of n different, or n plus 1 nodes or n plus 1 spaces, and you have n nodes in total. And the way it kind of works in practice is you, again, it's similar predictor corrector. You have your initial guess, which you start time stepping along, and then you use a essentially minimum stencil to get the next point, which you do in parallel, and then you keep getting points along, and then you go up to the next level, and it kind of keeps going like this. And so you essentially, I guess the goal is when you've got your j intervals, you want enough points in that such that you're not essentially always, so essentially everything has to sync up at the end. So you don't want to have too small an interval that is kind of inefficient. Part 3 results. Okay, so here I've got a mix of serial and parallel results all in one. So these are kind of standard dynamical core test pieces. So the first one is the one you would have seen yesterday in Josh's talk, which is the non-hydrostatic gravity wave. So essentially it simulates this 2D wave in a vertical slice, adding this initial perturbation to theta. It's kind of like dropping a pebble in a pond, and then your gravity waves kind of propagate outwards. You have an initial background wind of 20 meters per second, and it essentially tests your model's ability to capture wave propagation, speed, and structure. And the errors you're kind of looking for is dispersion errors, or you can kind of see these smaller scale waves. If you're using a semi-implicit method but are doing too much off-centering, then you end up damping these waves and getting rich. Okay, so these are the results. So this is only using zero SDC with fourth order, with LU and forward Euler Q delta matrices. And here I've used it as a high order convergence test in space and time. So I've kept CFL constant, and I'm varying both the order of the SDC scheme, and the order of the space radicalization, and doing a convergence test. So P is the order of the lowest order function space in the finite element family. So 1, 3, and 5. And for a convergence test here, so we've got second order when we're using 1, over fourth order when we're using 3, and over fifth order when we're using 5. So we get high order convergence using this. Good. And if you look at the solution, we're not kind of damping these small scale waves, and the solutions progress to the appropriate. The next test case is Williamson 1, if anyone knows Williamson 1. So this is shallow water, but it's not actually shallow water, it's just advection. And here we're actually using parallel in time stuff. So it's essentially this Gaussian blob in the sphere, and it just gets advected around and back to the same point over a period of 12 days. And here I'm running with a variety of schemes. So it's all explicit rather than IMEX. I've got SSP RK3, RK4, Riddick in third order, fourth order, and fifth order, and then serial SDC4 and parallel diagonal SDC4 using the non-stiff Q delta matrices. So here I've essentially got wall clock time versus normalized L2 error. And so if you look at Riddick 4 versus, where is RK4? RK4 here, we're essentially comfortably beating it in terms of wall clock time versus error. I've got Riddick 5 as well, which is also doing well, and Riddick 3 versus SSP RK3 is completely beating it. Or this is the kind of incomplete nature of it. STC4 and the parallelized version, you get some speed up between them. They're essentially using the same Q delta matrices, but they're quite slow and not doing as well as RK4 and SSP RK3. So I need to investigate that more. Okay, so the next test case includes moisture. So essentially, it simulates a moist thermal bubble in a saturated atmosphere. So it's testing essentially your moist thermodynamics and your coupling between your physics and your dynamics. And it's this kind of buoyancy driven nonlinear updraft. So the things that you're looking for in this test case is, so this is the original Bryan and Fitch paper. This is Tom Bendel's results with the lowest order finite element spaces and the next to lowest order. Here you can kind of spot, so you get this Rayleigh Taylor instability at the top. You get this small kind of nubbin that rises a little bit more, but this is common in the literature. So you're looking for kind of dispersion, damping errors, and errors in your physics. So on the other hand, with this one, so SIQN here is essentially the semi-implicit time stepping method. Riddick is top left, and then SDC using LU and FE, and the flex and non-stiff Q delta matrices. So essentially, with these three, we get symmetric bubble rises to the correct height, and they're using the next to lowest order spaces. So you kind of have this Rayleigh Taylor instability. Everything looks quite smooth at the moment. Semi-implicit quasi-Newton, it uses a different transport scheme. So it uses embedded GG instead of SUPG. And so you end up getting a little bit of noise around the top of the bubble. I currently have issues with Riddick, and I think it's likely to do with essentially the evaluation of the physics source terms. It's not evaluating them properly, and so it's not rising to the correct height. So this is further work. So the last test case, so common test piece in NDP is the baroclinic wave. And so it simulates essentially this mid-latitude cyclones that are triggered by this baroclinic instability. So you add a perturbation to the wind field, and essentially captures baroclinic instability and Rossby wave propagation. And here you've got these high and low pressure systems, so the cyclone, and kind of wave generated in the temperature field. So here you're looking for any kind of numerical errors with diffusion, resolution, time stepping. Okay, so for this, again, incomplete results. So here at the top, I've got IMX Riddick in parallel, semi-implicit quasi-Newton, and IMX STC, but in serial. At the moment, I only have access to one node of Archer 2, and so using time parallel STC, essentially, it blows up the memory, and I've already blown up it once, and everyone's access, it went down for a bit. It wasn't good. So here, if you look at the solutions, largely we're developing the same high and low pressure systems and the same kind of background temperature. The only real differences you can probably spot is the kind of down wave, as opposed to previously, you haven't really got any down wave oscillations in the pressure. Here you have a variety of different down wave oscillations. What I want to do with this test case in the future, I'm going to run it on the sphere, and I'm going to look at essentially error versus wall clock. But if you're looking at wall clock, semi-implicit quasi-Newton, which is a second order scheme, it's taking around like 9,400 seconds. Riddick is fourth order, but it is taking 11,000 seconds. STC is a lot slower at 23,000, but that is not in parallel. Okay. Summary. So IMX STC parallel IMX parallel diagonal STC and Riddick have been implemented in Gusto. We've looked at a bunch of different test cases to explore the viability of using these schemes to replace semi-implicit quasi-Newton for NWP and climate simulations. good solutions for most schemes. Riddick exams coupling needs fixing. And Riddick is competitive with SIQN and other standard time stepping schemes, but more investigations needed. At the top is a preprint of the serial paper if you're interested. I've got quite a lot of feature plans. Sorry, they all go at once. So in near time improvement to results, I want to fix issues with physics exams coupling for Riddick, focus on computational efficiency for parallel SDC, and I'd like to run the Barracklink wave with parallel diagonal SDC, but I can't do that at the moment. Longer term plans, work precision plots for gravity wave and Barracklink wave test cases, and scaling results for parallel deferred correction. Okay, thank you. Any questions?